Imagine for a second, just, picture yourself walking down the street in your city.
Right.
You pull out your phone, you book a taxi to get across town. Maybe you tap your digital bus pass at the transit station or
Or maybe you're just paying a local, municipal tax through a city portal while you wait for your coffee.
exactly.
Yeah.
Yeah, and it all feels just incredibly seamless. I mean, it feels like your city is just working for you, right?
Mhm.
Like it's intuitively anticipating your
It
needs.
does. It feels very smooth.
But imagine if behind the scenes you realize that almost every single one of those digital interactions, the data routing, the identity verification, the transaction processing, is secretly controlled by a few massive, invisible landlords.
And we aren't talking about the local city council here.
No, not at all. Not the Municipal Transit Authority either.
No, we're looking at private, highly centralized entities. I mean, the infrastructure that dictates the flow of urban life has, well, it's largely been outsourced.
Right. And to really put that into perspective, imagine if one single multinational tech company owned all the physical roads,
That would be wild.
like the traffic lights, the sidewalks in your town, all of it. And they dictated who could drive, what the speed limit was, and they monitored exactly where you walked at what time and, who you were with.
People would revolt. I mean, you wouldn't accept that in the physical world for a second. The monopoly on movement would be terrifying.
Totally terrifying. So why do we just accept it without a second thought for our digital infrastructure?
It's a profound contradiction, and it stems from a trade-off we've made almost unconsciously, really, over the last decade.
Convenience factor.
Exactly. We like the convenience. We like that the digital roads are paved, they're ultra fast, and they rarely have potholes. But because we don't, experience the digital infrastructure physically, we rarely stop to look at who actually holds the deed to the property we're traveling on.
That is such a good point. Well, welcome to this deep dive. Today, we are taking you into the hidden architecture of the smart city. We have a really fascinating mission today.
We do. We're unpacking a highly comprehensive 2026 study.
Yep, from the journal Pervasive and Mobile Computing. And this research, it looks at the silent battle for the soul of our cities. It's an exploration of the tension between centralized big tech monopolies and this radical emerging alternative.
Right. The decentralized peer-to-peer or PDP infrastructure.
Exactly. So we are going to figure out who actually owns the smart part of our cities, what the hidden risks of that ownership are, and how emerging technologies might actually give control and ownership back to you.
And what's particularly striking about this tension, I think, is the historical irony of it all.
Oh, yeah. The original vision of the internet.
Right. The foundational architecture designed in the late 20th century was exactly the opposite of the smart city model we have today. The internet's pioneers built it on strict principles of openness and, well, decentralized management.
It was supposed to be a web.
Exactly, an end-to-end network where the intelligence lived at the edges with the users. No one central entity was supposed to mediate every single interaction.
But then the cloud happened.
Yeah. Over the last 15 years, the convenience of the cloud has driven a massive consolidation. The top layers of the internet, the application and service layers that actually run our cities, have been aggressively consolidated into the hands of just a few dominant cloud providers.
It really is a complete 180 from the original dream. I mean, we've essentially rebuilt the mainframe model just on a global scale.
That's a great way to put it.
But before we can really debate who should control the smart city or, how to rebuild it, I think we need to understand how a smart city is actually built in the first place.
Right, we have to look under the hood.
Yeah, because when I tap that taxi app, it feels like a simple command. But according to this study, I'm actually interacting with a deeply stratified matrix of technologies. Like, I don't want to trace the life of that single tap, what is actually happening there.
So, to understand the sheer scale of the operation, system architects divide the city's digital ecosystem into an interconnected stack.
Okay, like a layer cake.
Pretty much. At the foundational level, you have the physical realm interacting with the digital. This is the Internet of Things, the hardware.
So cameras, sensors, that kind of thing.
Exactly. When you're standing on that street corner, there are sensors all around you detecting traffic flow, actuators controlling the timing of the streetlights based on congestion, ambient weather sensors, localized cellular antennas.
Wow.
These devices are the nervous system of the city, a constantly translating physical reality into digital telemetry.
Okay, so the city is constantly observing its own physical state, the temperature, the traffic, the air quality. But that raw telemetry isn't useful on its own, is it?
No, not at all. It's just noise until it's processed.
Right.
That raw data has to flow upward into repositories. So right above the hardware layer, you have massive data lakes and relational databases.
And are these public or private?
Both, actually. Some are public, like real-time transit schedules or weather patterns, and some are highly siloed and localized to specific services, like a hospital's intake database or a private fleet's location tracking. But again, raw data, even organized in a database, doesn't book you a taxi.
Right, because my app needs to know way more than just, hey, there's a car on Fifth Avenue. It
Exactly.
needs to know if that car is empty, if the driver's licensed, and, how much it will cost to get me home.
Which brings us to the core engine of the smart city, the business logic. This is the software layer that does the heavy lifting.
Okay, so this is where the magic happens.
Yeah, it takes the static data and applies complex algorithms to it. When your app requests a taxi, it triggers an identity verification service to ensure your account is in good standing. It hits a geolocation routing service that calculates the optimal path, factoring in the real-time traffic data pulled from the hardware layer.
Oh, wow, so it's talking to the sensors.
Right. Then it queries a dynamic pricing engine. All of this orchestration happens across dozens of microservices before it finally surfaces a result.
And then finally, that result hits the screen on my phone,
Yeah.
the user interface layer.
Yes. The user app layer, the only part of this massive iceberg that you actually perceive.
That's incredible. To me, it's literally just a single tap, a half-second pause, and then a confirmation screen.
Right, but in that half second, your request has traversed physical sensors, queried massive databases, executed complex algorithmic logic across distributed servers, and returned a highly personalized result.
It is a staggering orchestration of interoperable services. I mean, it's like a single tap on my phone is essentially conducting an orchestra of different technologies across the entire city.
It is, but here's the crux of the issue the study raises. This orchestration is a miracle of modern engineering, sure, but it relies on a conductor.
Ah, right, the invisible landlord.
Exactly. If I'm using a smart city service, let's say a municipal transit app,
Yeah.
and it's pulling from mapping APIs, identity verification servers, and payment gateways, there is a very high probability that all of those disparate microservices are physically running on servers owned by one or two global tech giants.
Right. Amazon Web Services, Google Cloud, Microsoft Azure.
Yes. And that is the architectural reality we're dealing with. If we connect this to the bigger picture, a smart city isn't a monolith. It's an ecosystem of interoperable services. And that raises an important question. What happens if the conductor of this orchestra is a single, profit-driven corporate entity?
Well, the city inherently loses its digital sovereignty, doesn't it? It becomes a tenant on someone else's land. Just think about how many unseen background services your apps trigger just on your morning commute.
Hundreds. Thousands, even.
And we really need to grasp the sheer scale and capability of these dominant players, because it perfectly explains why cities have willingly become tenants in the first place. I mean, a local municipality just doesn't have the budget to build a world-class data center.
No, of course not. And the tech giants offer a product that is, frankly, unbelievable.
It really is. The study notes some of these performance metrics, and they are staggering. We are talking about Google processing upwards of 24 petabytes of data daily.
That number is almost hard to comprehend.
It is. And Microsoft Azure is delivering round-trip network latencies from Western Europe to the Western U.S. in just 154 milliseconds.
Let's contextualize that latency, right?
All right.
154 milliseconds to send a packet of data across the Atlantic Ocean, route it through complex data center architecture, and receive a response back.
Faster than a literal blink of an eye.
Exactly.
Yeah.
That is undeniable technical maturity. From the perspective of a city council looking to digitize their local services, the decision seems obvious.
Yeah, why spend tens of millions of taxpayer dollars trying to build local server infrastructure?
And hire cybersecurity teams and maintain uptime.
Right. When you can just sign a contract with a centralized cloud provider who offers a turnkey solution with, like, 99.99% guaranteed uptime.
It's the path of least resistance. It's incredibly fast, it's hyper-reliable, and in the short term, it's cost-effective.
But we're trading long-term resilience for short-term speed, aren't we? The researchers are arguing that using technical performance as the sole metric for architectural decisions in a smart city is a massive mistake.
A huge mistake. Because right now, two cloud providers control over 50% of the global market.
Just two.
Yes. And that level of centralization creates severe structural vulnerabilities for a society. It creates a brittle system.
What's the immediate risks there, like the economic risk?
Let's look at vendor lock-in. When a city builds its digital infrastructure, its traffic management, its public records, its emergency response routing on proprietary tech from a single cloud provider, they are adopting that provider's specific databases, their proprietary APIs, their unique data structures.
So they're completely entangled.
Completely. If that provider decides to double their pricing 5 years down the line, the city is trapped. The technical friction and the financial cost of migrating an entire city's digital operations to a competitor are astronomical.
Wow. It effectively stifles local innovation too, doesn't it? Like, if I'm a local developer in my city trying to build a new civic application, I can't just plug into the city's data if it's all locked behind a proprietary tech giant's ecosystem.
Exactly. You're boxed out by the monopoly. Monopolies crush fair competition.
But beyond the economics, there's a fundamental philosophical issue here about the business models of these centralized entities. Here's where it gets really interesting. We trade our city's digital independence for convenience because big tech servers are incredibly fast and reliable. So we are basically paying rent with our personal data.
That is the core conflict of interest. The study highlights that the predominant business model of the centralized internet is data monetization. We know that massive platforms like Meta derive up to 97% of their revenue from targeted advertising.
97%. That is wild.
So, when a smart city uses centralized identity verification or data storage services, they're integrating with a system engineered to extract data. It treats citizen data, where you go, what transit you use, when you pay your taxes, not as a public good to be protected, but as an asset to be harvested, analyzed, and monetized.
We get the shiny, fast app, but the landlord gets an omnipresent view of our civic lives.
Yes.
And it's not just about privacy and surveillance, is it? It's about sheer operational resilience. When you centralize infrastructure, you create massive single points of failure.
Right. If a local server goes down in a decentralized system, maybe one neighborhood loses transit updates for an hour.
But if a massive centralized cloud provider has an outage, say, a data center goes down due to an extreme heat wave.
Which we have seen happen repeatedly in recent years.
Exactly. Entire swaths of a city's critical infrastructure can simply vanish from the internet. Just poof, gone.
And that operational fragility extends into the geopolitical realm as well. This is what the researchers term the risk of internet consolidation. When a centralized authority controls the digital roads, they have the absolute power to close them.
The study brings up a really compelling recent example of this, the ban of the social platform X in Brazil.
Yes, a very relevant case study.
Right. And, regardless of where anyone stands on the politics of that specific dispute between the platform and the Brazilian Supreme Court, the underlying technical reality is what's fascinating. Because the architecture of that network is entirely centralized, a legal dispute at the very top resulted in millions of citizens instantaneously losing access.
They lost access to their accounts, their business networks, their social graphs. A switch was flipped, and the service ceased to exist for an entire country.
Just like that.
It perfectly illustrates the inherent power dynamic of the hub-and-spoke model. In a centralized architecture, the hub mediates absolutely everything. It routes the traffic, it holds the cryptographic keys, it claims ownership of the data state, and it acts as the ultimate arbiter of access.
And regulatory bodies around the world are waking up to this imbalance, right?
They are. We see the European Union attempting to enforce the Digital Markets Act to force large platforms to interoperate, or the U.S. Justice Department exploring antitrust actions to consider breaking up Google.
But the law moves at a glacial pace compared to technology. I mean, trying to regulate a centralized monopoly feels a bit like putting a Band-Aid on a structural flaw.
It is. The hub-and-spoke model fundamentally resists distributed control because the physics of its code demands centralization.
So if we truly want to escape this dynamic, if we don't want massive corporations acting as the omnipotent mediators of our urban lives, how do we build a city that runs itself? We have to look at the alternative. How do we actually build a city digital infrastructure that doesn't rely on a hub?
We have to shift our paradigm entirely toward decentralized, peer-to-peer, or P2P architectures. And to understand the mechanics of this, it really helps to look at the first time this concept was stress-tested at a global scale. We need to look back at the late 90s.
Okay, taking us back.
Specifically the emergence of platforms like Napster and eventually BitTorrent.
Ah, the Wild West of the early internet. But we aren't talking about illegally downloading MP3s anymore. What did those early networks actually prove about infrastructure?
They proved that a network could function without a central server storing the data. In a true P2P network, the participants are simultaneously both clients and servers. You aren't connecting to a massive data center to request a file.
So what are you connecting to?
The network is an overlay created by all the participating devices. You request data, and your device pulls fragments of that data directly from the devices of other users who happen to hold it. And simultaneously, you're uploading fragments you hold to others who need them.
Okay, let's break this down because the mechanism here is so crucial. In the centralized hub and spoke model, if I need to find a piece of information, say, the current location of the downtown bus my phone asks the central server. The central server looks at its map, finds the bus, and tells me.
Exactly.
So instead of it going through a central post office that opens and reads every letter to monetize your habits, P2P is like everyone in the city agreeing to hand-deliver mail to their neighbors directly.
That's a perfect analogy.
But wait, if we rip out the post office and go P2P, how does my phone actually find the bus? If there's no central map and everyone's phone is constantly moving and changing IP addresses, how does the network not just collapse into total chaos?
That is the defining engineering challenge of P2P networks, and it's solved through incredibly elegant mathematical routing. Because there is no central map, the network relies on the required software stack for P2P, specifically things like distributed hash tables, or DHTs, and gossip protocols.
Gossip protocols. I love that name.
Yeah.
That sounds like high school.
The analogy is actually very apt. Imagine you are in a massive, crowded stadium, and you're trying to find someone named Dave.
Okay, looking for Dave.
But you don't know where he sits, and you don't have a central directory to consult. So you turn to the three people immediately next to you and ask, do you know where Dave is, or do you know someone who might know?
Okay.
They don't know, so they turn to the three people next to them and ask the exact same question. The request ripples outward exponentially. Eventually, someone who knows Dave's location receives the message, and the path back to you is established.
Oh, wow. So the network uses the connections between the peers themselves to route the query rather than relying on an omniscient central database.
Exactly. It hides the dynamic topology of the network. Peer discovery and routing happen organically. But instead of names like Dave, these networks use cryptographic hashes to identify data.
Right, the hash table.
Precisely. A distributed hash table assigns a unique cryptographic identifier, a hash to both the data and the devices on the network. When you search for a specific piece of data, the network mathematically routes your request to the device whose identifier is closest to the data's identifier.
That's wild. It's a way of organizing a chaotic, constantly shifting network of millions of devices into a mathematically predictable structure, entirely without a central coordinator.
And without needing a central server for replication either.
And this isn't just an abstract theory anymore. The study points out that the software stack required to run these decentralized networks has matured significantly. I mean, we are seeing it challenge the centralized giants in real time.
We really are. Look at the social media landscape with the rise of the Fediverse. Platforms like Mastodon, Bluesky, and Diaspora, they operate on decentralized protocols. You don't have one company owning all the servers. You have a network of independent servers communicating with each other.
Right, and it extends deep into the infrastructure layer, too.
Yes. Instead of developers relying on Amazon S3 for centralized data storage, they can utilize systems like IPFS, the Interplanetary File System.
Great name, by the way.
It is. IPFS breaks data down and distributes it across a global P2P network. And for real-time video or audio communication without a mediating server routing the call, developers use the WebRTC standard.
Oh, right, for browser-to-browser communication.
Exactly. The foundational tools to bypass the hub are available.
Okay, so I understand the routing. I understand how we find the data using DHTs and gossip protocols, but there is a massive glaring issue here that we haven't addressed. Trust.
Ah, yes.
The trust problem.
Right. I mean, if I'm using a centralized app to book a taxi, I trust the platform. I trust that the platform has verified the driver's license and background check. If you're completely bypassing the central authority and connecting peer-to-peer, how do we trust our neighbors? How do I know the device I'm connecting to isn't malicious?
It's a very valid concern. Because if there is no central server verifying identities, what stops someone from pretending to be the city transit authority and feeding my phone fake bus schedules? Or worse, pretending to be my bank?
You've hit on the most critical vulnerability of a decentralized system. In a centralized paradigm, trust is delegated entirely to the provider. You trust Google to be Google.
Right.
In a decentralized system, trust must be shifted away from an institution and placed into mathematics, specifically cryptography and community verification.
But even cryptography requires a baseline of trust right now, doesn't it? When I go to a secure website, my browser trusts it because a centralized certificate authority, a massive company like VeriSign, vouched for it.
Right.
So if we are decentralizing, we have to decentralize the root of trust itself.
Exactly. The current public key infrastructure of the internet still relies on a global oligopoly of certificate authorities. If one of those central authorities is compromised, the security of the whole system shatters. The researchers in this study point to emerging decentralized architectures designed to fix this, utilizing decentralized roots of trust. They specifically highlight the SC-ION Secure Internet Architecture.
SC-ION. Walk me through how that works. If my phone needs to verify the identity of a municipal service in a P2P network, how does SC-ION do it without asking a global authority?
SC-ION re-engineers the internet's routing and trust model by introducing the concept of isolation domains.
Isolation domain.
Yes. Instead of relying on a few global authorities that have total jurisdiction, the internet is broken down into localized, logically distinct domains. Trust is scoped locally. When two peers within or across these domains want to communicate, they use cryptographic proofs that can be verified independently.
So instead of needing a global stamp of approval from a massive tech company, my device can mathematically verify the cryptographic signature of the local transit authority directly, based on a chain of trust established within our specific city's domain.
Correct. You establish secure, authenticated communication directly between peers. You verify credentials locally without a global mediator having the power to intercept, spoof, or revoke that trust arbitrarily.
Okay, so the theory is robust. We have DHTs for routing, IPFS for storage, and architectures like SC-ION for decentralized trust. But theory is clean, and cities are messy.
Very messy.
I want to know what happens when you take these pristine cryptographic concepts and try to lay them over the bureaucratic, chaotic reality of a physical city.
Well, the study actually gives us a brilliant case study of this. It's a real-world pilot project happening right now in Santa Rosa, a municipality in Brazil.
Oh, nice.
The Santa Rosa pilot is an incredible sandbox for these technologies because it deals with the exact friction you just mentioned. The municipality wants to build a cohesive, smart city experience for its citizens. They want to digitize healthcare, education, taxation, and law enforcement. But they face a classic infrastructural nightmare.
Let me guess. Legacy silos.
Legacy, non-interoperable technology silos, yes.
Right. The health department built their database in 2005 using one proprietary vendor. The education department uses a completely different system from 2012. And the tax authority uses something else entirely. None of these systems were designed to interoperate. They speak completely different digital languages.
Exactly. And the traditional centralized solution to this problem is to build a massive central integration server. You force all the departments to dump their data into one central hub so they can communicate. But the moment you propose that, you run into insurmountable privacy and security roadblocks.
Oh, for sure. Because the health department holds incredibly sensitive patient records. They are legally and ethically bound not to just hand over copies of raw medical data to a central city server that might be vulnerable to a cyber attack.
Or accessed by employees in the tax department.
Right.
The silos exist for a reason. They naturally compartmentalize risk. So the researchers in Santa Rosa asked, how do we achieve the interoperability of a smart city without creating the massive honeypot of a centralized database?
And what do they find?
They realized they had to start at the very foundation of any interaction, identity. Before a citizen can use any service, they must prove who they are.
Well, if they take the easy route, they just integrate a centralized login. They let citizens access city services using their Google or Meta accounts, or even a centralized government ID like Brazil's GovBR.
But doing that immediately reintroduces the monopoly problem. You are injecting big tech surveillance directly into local municipal infrastructure. If you log into the local tax portal with a centralized tech ID, that tech company now has a data point about your financial activities.
Yeah, we definitely don't want that. So what is the decentralized alternative for identity? How do I prove who I am to the city without checking in with a central tech giant?
The alternative is a paradigm called self-sovereign identity, or SSI. The Santa Rosa pilot is actively testing SSI frameworks utilizing systems like Trust Chain.
Trust chain, okay.
SSI completely flips the traditional power dynamic of identity verification. In a centralized system, a corporation holds all your data on their server, and when you try to log in, they verify you against their records. In an SSI model, you hold your own verified credentials locally on your own device, usually in a secure digital wallet.
Let's make this tangible. I love the analogy of identity as a bouncer at a club.
It's a great analogy.
Let's say I'm trying to access a municipal service that is only available to residents of Santa Rosa who are over the age of 18.
Hmm.
In the physical world, or the centralized digital world, I would hand the bouncer my driver's license.
Right. And when you hand over that driver's license, you are oversharing a massive amount of data. You are showing the bouncer your exact date of birth, your full legal name, your precise home address, your organ donor status, your height, your eye color.
All to answer a simple yes or no question. Are you over 18?
Exactly. It's a massive privacy leak disguised as a routine transaction. But with self-sovereign identity, my digital wallet acts like a highly sophisticated, localized bouncer. Instead of handing over the whole card, the service queries my wallet. Is this person over 18? And my wallet uses cryptography to generate a proof, a mathematical guarantee that the answer is yes.
So what does this all mean? It means your identity acts like a highly selective bouncer. You only show the exact piece of information needed for that specific interaction and nothing more. It sends that proof and absolutely nothing else.
That concept is known in cybersecurity as data minimization, and it is a core pillar of privacy by design. The service gets the exact authorization it needs, but it never learns your exact birth date, your name, or your address. You remain entirely sovereign over your raw data. This approach inherently prevents mass surveillance and data harvesting.
By implementing privacy by design at the very foundation of the city's infrastructure.
Exactly.
That is incredibly elegant for the user interaction. But let's go back to the friction between the city departments. Let's say the identity is sorted. How do the departments collaborate on complex civic issues without exposing their raw data to each other? Let's take a hypothetical scenario. Let's say the city wants to know if poor air quality in a specific industrial neighborhood is correlating with an increase in childhood asthma.
It's a perfect example. To figure that out, you need data from two silos. The Environmental Protection Department has the granular air quality sensor data, and the Public Health Department has the pediatric medical records. Neither department trusts the other enough, or is legally allowed, to hand over their raw database.
Right. They operate on a model of mutual distrust. The departments want to share health data for insights, but don't want the integration system to keep copies of sensitive data.
Yes.
So if they can't share the data, and they can't upload it to a central hub, how do they run the correlation?
They utilize an advanced branch of privacy-enhancing technologies, PETs for short, specifically something called Secure Multi-Party Computation, or SMPC.
SMPC. I have to admit, secure multi-party computation sounds a bit like computational magic.
It kind of is.
How on earth do you compute a statistical analysis across two databases without either database actually seeing the other's numbers?
It relies on cryptographic secret sharing. The mathematical mechanics are complex, but the underlying logic is brilliant. Instead of sharing the actual data, SMPC breaks the data down into mathematical fragments, or shards, that look like completely random, meaningless noise. These random shards are distributed across the participating parties.
Wait, so the environmental department receives shards of the health data, but because it's just random noise, they can't reverse engineer it to see a child's medical file?
Exactly. The shards are useless in isolation. But because of the specific cryptographic properties of how the shards were generated, the departments can run mathematical functions like additions or multiplications directly on the random noise.
That's crazy.
They compute the analysis jointly across the network. When the computation is finished, the final result is reconstructed, and the statistical correlation is revealed.
So at the end of the process, they get the answer. Yes, there is a 20% spike in asthma in this specific zip code. But the environmental department never saw a single medical file, and the health department never saw the raw sensor data.
Never. The data is protected not just when it's sitting in storage or when it's moving across a network, but it's protected during execution. That completely dismantles the need for mass surveillance and data pooling. It proves that a city can be highly intelligent and data-driven without resorting to centralized data harvesting. You can bake privacy into the very mathematics of the city's infrastructure.
Okay, so we have SSI for identity, and we have SMPC for interdepartmental privacy. But let's look at the actual exchange of a service. Proving who I am is great, but that doesn't actually get me on the bus.
Right, access control.
Yeah. If there is no central server to process my transaction, how does a decentralized system handle a physical exchange of value? Let's say I buy a 10-ride digital bus pass. In the world we live in now, that bus pass is just an entry in a database on the Transit Authority's central server. When I board the bus and tap my phone asks the server, does he have rides left? The server checks the database, deducts one ride, says yes, and the turnstile opens.
Right, and if the transit server is down for maintenance or there's a network outage, you don't get on the bus, even if you've already paid for the rides. Your access is contingent on a live connection to the hub.
So how does decentralization solve the bus ticket problem? Because you can't just give me a digital file. In the digital world, I can copy a file a million times. If my bus ticket is just a file on my phone, I'll copy it and ride for free forever.
This brings us to a fascinating area of computer science regarding access control. To solve this, the researchers lean on a concept originally formalized by a computer scientist named Nick Szabo, the idea of scarce objects.
Scarce objects.
As you noted, data is inherently abundant and perfectly reproducible. A decentralized smart city has to figure out how to create artificial scarcity for things like tickets, licenses, or access tokens.
It has to make a digital object behave like a physical object. Like if I have a paper bus ticket and I give it to the driver, I don't have it anymore.
Precisely. To achieve this, the architecture combines scarce objects with a localized security model called capabilities. In a traditional system, the central server uses an access control list to dictate who gets in. In a capability-based system, the permission isn't on a server. It's a cryptographic token held directly by the user. Your 10-ride bus pass is engineered as a stateful, scarce object.
Stateful meaning it has a memory of its own condition. It knows it has 10 rides, then it updates itself to know it has 9.
Yes, the pass literally lives on the local hardware of your phone. When you board the bus, your phone interacts directly with the turnstile's hardware in a localized peer-to-peer exchange. It doesn't need to route a request to a central server downtown. The turnstile cryptographically verifies your capability token, and the scarce object on your phone updates its state locally to 9 rides.
Wow! Think about that. Look at your phone right now. In a centralized system, that expensive computer in your pocket is essentially just a dumb terminal begging a distant server for permission to do anything. In a decentralized system running a scarce object, your phone actually physically holds the asset.
Right.
The power dynamic is completely inverted.
And because it is a localized capability, it unlocks entirely new organic ways for citizens to interact. If you have 9 rides left on your phone and a friend needs a ride, you don't have to log into a central transit portal, navigate to a family sharing tab, and wait for a server to process a transfer.
Oh, I see where this is going.
You can use a peer-to-peer protocol to digitally hand one of your rides directly to your friend's device. You delegate the capability locally without asking a central server for permission.
It's exactly like handing them a physical paper ticket out of your wallet.
Yes.
That is the essence of true digital sovereignty. The asset is yours to control, completely independent of a corporate mediator.
It is a beautiful vision of civic autonomy, but we cannot ignore the immense technical complexity it introduces. If that scarce object is completely decentralized, how does the network ensure you don't double spend it? What stops you from using a modified software client to send that same digital ticket to 2 different friends at the exact same millisecond before the network updates?
Okay. Because there is no central database to act as the ultimate referee and say, no, he already spent that.
Exactly. To prevent double spending in a P2P network, you require highly robust consensus algorithms. The participating nodes in the local network, the turnstiles, the transit vehicles, the nearby civic servers, have to rapidly reach a mathematical agreement on the true state of that object.
Yeah.
That requires significant computational overhead.
It's all starting to come together into a coherent picture. We can decentralize identity, we can protect private department data, and we can manage access to services directly. But there is one massive piece of the smart city puzzle left. Well, a city doesn't just run on private data. It requires a massive ocean of open public data to function. Think of the real-time GPS locations of every city bus, the structural integrity sensor data from public bridges, or the localized weather telemetry. If big tech isn't harvesting and storing our data, and departments are keeping it secure, who actually looks after the massive pool of open data a smart city needs to function?
This is a vital question of governance. If data is the lifeblood of the smart city, who owns the blood bank?
Exactly.
The researchers point to a framework heavily championed by organizations like the Open Data Institute, the concept of data trusts. This represents a total paradigm shift in how we view digital resources. Currently, municipal data is often treated either as a proprietary asset to be guarded, or worse, as a product to be sold.
Right, treating city data not as an asset for sale, but as a public commodity. I mean, cities are constantly strapped for cash. It's incredibly tempting to sign a deal with a tech company where the city hands over the exclusive rights to its transit data in exchange for the tech company installing free Wi-Fi kiosks on the sidewalks.
And we see that happening.
The city gets a visible win for the voters, but they've quietly privatized a public resource.
The data trust model aggressively pushes back against that privatization. It argues that non-sensitive infrastructural city data must be legally classified and treated as a public commodity. The most intuitive parallel is how we handle physical public spaces.
Like municipal parks or conservation areas.
Exactly. Compare data trusts to land trusts that manage physical public parks. Independent entities take on a fiduciary duty to steward the data with impartiality and transparency.
So they don't own it to exploit it. They hold it in trust for the benefit of the community.
Exactly. A data trust applies that exact legal and ethical framework to digital assets. The trust acts as an independent, legally recognized intermediary. It is governed by a board that has a strict fiduciary responsibility to steward the communal data impartially and transparently. The data isn't locked in a proprietary AWS server. It is hosted openly. Services pay for the rights to access the data, not to own it.
So how does a developer actually build an app using that data? Let's say I'm an entrepreneur in Santa Rosa, and I want to build a better, more accessible routing app for visually impaired citizens using the city's transit data.
Under the trust model, you don't have to negotiate a massive licensing deal with Google to access the city's data. You approach the data trust. The trust grants you the rights to access the data through open APIs under clearly defined terms that protect the public interest. You might pay a nominal access fee to help maintain the infrastructure, but you don't buy the data itself.
So to clarify for you listening, it's like paying an entry fee to a beautiful botanical garden. You get to enjoy the garden, maybe take some photos, maybe set up an easel and paint a picture of the landscape to sell. You can build a business around the garden, but you absolutely do not get to dig up the rare flowers and take them home to sell.
A perfect parallel. The resource remains intact for everyone. And from an economic standpoint, this model is absolutely critical for activating local innovation. When data is siloed and hoarded by global monopolies, the barrier to entry for civic tech is insurmountable. A local small to medium enterprise, an SME in Brazil, simply cannot compete with the data-gathering apparatus of a trillion-dollar tech giant.
But if the foundational data is held in a public trust, accessible via open standards, the playing field is leveled. That local developer in Santa Rosa can build a hyper-localized app that perfectly serves their community without being boxed out by global monopolies.
Exactly. That is the ultimate economic argument of the study. Treating data as communal wealth governed by a trust is the only sustainable way to build a smart city ecosystem that is actually inclusive and economically vibrant for its own residents.
Okay, I have to stop us here, because I'm listening to this and everything we have unpacked, self-sovereign identity, putting the bouncer in my pocket, SMPC computing statistics on invisible data, peer-to-peer bus passes, democratic data trusts, it all sounds incredible. It paints a picture of a digital techno-utopia. What are the major roadblocks stopping every city from doing this tomorrow?
The catch is substantial, and the researchers are incredibly intellectually honest about it. We have to present the conflicting viewpoints and limitations impartially. Decentralization is not a simple fix. It is a trade-off, and the hurdles to large-scale deployment are massive.
Okay, let's look at this impartially. What's the first roadblock?
The first and most glaring roadblock is performance and predictability.
Right, we talked earlier about Google's 154 millisecond latency. A centralized architecture is a highly controlled, optimized, predictable environment. You own the fiber optic cables, you own the servers, you control the load balancing. It's an autobahn. PDP networks, by definition, are chaotic.
They are inherently unstable environments. Think about the physical composition of a localized P2P network. You are relying on a mesh of heterogeneous resources. You have a massive municipal server communicating with a high-end smartphone, which is communicating with a tiny low-power IoT sensor embedded in a parking meter. You don't have a central boss orchestrating the traffic flow.
And the participants are constantly vanishing. If I'm a node in the network and I walk into a subway tunnel, I just dropped off. If my battery dies, I'm gone.
That phenomenon is known as peer churn nodes, joining and leaving constantly. The topology of the network is changing second by second. When you try to route a complex query through a constantly shifting landscape of unpredictable devices, you introduce significant latency. Despite the advances in DHTs and gossip protocols, currently, decentralized networks simply cannot match the guaranteed ultra-low deterministic latencies of an Amazon or Google data center.
So in practical terms, you might tap your digital bus pass at the turnstile and have to stand there awkwardly for 4 or 5 seconds while the local peer-to-peer network attempts to reach consensus and verify your scarce object. Whereas a centralized system would have opened the gate in a fraction of a second.
Exactly. And in urban environments, milliseconds matter. That friction leads directly to the second major hurdle: adoption and network effects. We have to face reality. Centralized platforms win because of massive user bases. The barrier to entry is zero. You download the app, you click Login with Google, and you are done. The barrier to entry for decentralized platforms is currently massive.
And decentralized platforms have high usability barriers. I mean, users have to manage their own identities and servers. Look at the attempts to migrate people off centralized social media onto decentralized platforms like Mastodon. People get frustrated by the algorithms, they decide to leave, they download Mastodon, and immediately they are asked to choose an instance, understand federation, and manage their own cryptographic keys. They get overwhelmed and they go right back to the centralized platform.
The usability gap is a severe bottleneck for civic adoption. If a smart city requires its citizens to actively manage their own SSI wallets and act as nodes in a P2P network, a massive portion of the population will simply be left behind. But even if you solve usability, you have to confront the third major roadblock: security threats.
Wait, didn't we establish that decentralization enhances security by removing the central honeypot?
It removes the central honeypot, yes, but it introduces entirely new vectors of attack unique to permissionless networks. When you have a network where anyone can join and there is no central authority verifying real-world identities, the system is vulnerable to structural manipulation. Two of the most prominent threats in P2P architecture are Sybil attacks and Eclipse attacks.
Let's break those down because they are critical to understand.
Yeah.
What exactly is a Sybil attack? If anyone can join anonymously, what's stopping a malicious actor, say a coordinated hacking group, from just spinning up 10,000 fake virtual phones on a server farm and joining the city's network?
You've just perfectly described a Sybil attack. The attacker generates a massive number of fake pseudonymous identities, Sybil nodes, and floods the P2P network. Because many decentralized consensus mechanisms rely on voting or collective agreement among peers, these fake nodes can outvote the honest nodes. They can alter routing tables, censor specific data, or even force the network to agree on a fraudulent transaction.
That is terrifying. If a network relies on community consensus, a Sybil attack is basically ballot stuffing on an industrial scale. So how do you fight that without requiring a central authority to check everyone's ID?
It requires complex, localized reputation systems or cryptographic resource-proving mechanisms, but those are notoriously difficult to scale without inadvertently reintroducing forms of centralization, and the threats get more targeted. The other major vulnerability is an Eclipse attack.
How does an Eclipse attack work?
While a Sybil attack floods the whole network, an Eclipse attack isolates a specific target. The attacker manipulates the routing tables of the P2P network to surround a specific honest node, say your specific smartphone, or a specific traffic control sensor. They ensure that every single connection your device attempts to make is intercepted by a malicious node controlled by the attacker.
They eclipse my view of the real network. I think I'm talking to the city, but I'm trapped in a bubble of malicious keys, which means they can feed my device entirely fabricated data or block my transactions from ever reaching the real network.
Precisely. And alongside these active attacks, you also have the passive problem of free riders.
Free riders?
Yes. P2P networks rely on mutual contribution. If a large percentage of citizens modify their devices to consume the network's bandwidth and data without contributing any of their own processing power or storage back to the community, the network starves and collapses. They drain network resources.
So ditching the landlord means we have to become our own plumbers, electricians, and security guards. And if the roof leaks, there's no 1-800 number to call. Which leads me to what seems like the most intractable problem for a physical municipality: liability.
This raises an important question. Who is legally accountable when a decentralized service fails? Existing regulatory frameworks demand a clearly identifiable legal entity to take responsibility, which P2P networks inherently lack.
Right. If the centralized traffic routing server goes down due to negligence and it causes massive gridlock and accidents, the city council knows exactly who to sue. They sue the cloud provider for breach of contract. But if a decentralized peer-to-peer traffic network goes down, who's legally accountable? Do you sue the collective neighborhood? Do you sue the open source developers who wrote the protocol?
You cannot issue a subpoena to a decentralized protocol. If there is a catastrophic service failure, attributing legal and financial responsibility in a fully decentralized architecture is an unresolved legal nightmare. And that brings us to the financial reality. Centralized cloud providers offer predictable pricing. A city signs a multi-year contract for $5 million a year, and the budget is set.
In a P2P network, the operational costs don't just magically disappear. They are shifted.
They are shifted onto the participants. Citizens implicitly pay by donating their devices' bandwidth and battery to sustain the civic network. Furthermore, the municipalities must fund the core infrastructure, manage the data trusts, and facilitate the standard setting without a proven, profitable business model. There is no massive advertising revenue engine subsidizing a decentralized municipal network.
It is a sobering reality check. We have latency issues, massive usability gaps, civil attacks, free riders, and a total lack of legal accountability.
Knowing these massive structural hurdles, how do the architects of tomorrow's cities actually move forward? Is the decentralized smart city just a hopeless academic exercise? The researchers absolutely do not believe it is hopeless. They conclude their study with a very concrete four-dimension guideline. It is a pragmatic blueprint for action designed specifically to bridge the gap between this experimental technology and large-scale, resilient deployment. But it requires highly coordinated effort across four distinct groups.
Let's walk through this blueprint. How do we actually build this?
First dimension, the researchers.
Okay, the academics and the engineers. What is their mandate to fix the flaws we just discussed?
The researchers must aggressively move beyond theoretical models. Their mandate is large-scale stress testing in chaotic environments. They have to mature the software stack by creating standardized, robust APIs. And most importantly, they have to solve the consensus bottlenecks.
They have to make it fast enough to compete with the centralized giants.
Exactly. Dimension 2, system architects.
These are the people actually writing the code and building the digital roads for the city.
Their core directive is to prioritize open-source components above all else. They must militantly avoid proprietary software that leads to vendor lock-in. When they design a new municipal system, they need to design for resilience using P2P protocols from the ground up.
Okay, but the engineers can't do it alone because none of this works if the legal reality doesn't support the code. That brings us to Dimension 3, right?
Yes. Dimension 3, policymakers. Policymakers have a foundational role in this transition. They must write data sovereignty into law. They need to create the legal frameworks that allow data trusts to exist. Crucially, they must mandate open standards for public procurement.
Meaning, they pass laws saying a city cannot legally purchase or implement a software system using taxpayer money unless it interoperates with open APIs.
Exactly. And they need to be willing to regulate local digital monopolies, preventing a single corporation from capturing the critical infrastructure of a municipality.
And finally, Dimension 4, city authorities, the mayors, the city councils.
They must fundamentally shift their perspective. They must treat citizens as data owners.
They need to be willing to experiment, too. They can't just sign the easy contract with AWS.
Right. They must use experimental sandboxes, like the Smart Live Lab pilot in Santa Rosa, where these decentralized technologies can be tested safely. And they must form partnerships with local universities, rather than just signing contracts with massive tech vendors.
It's a massive group project. The politicians have to write the rules, the researchers have to build the tools, the architects have to draw the blueprints, and the city managers have to actually trust the citizens with the keys.
If we synthesize the ultimate takeaway of this exhaustive study, it is this. The transition to a decentralized smart city isn't just a technical upgrade, it is a fundamental shift in civic power. The choice of API or database architecture is deeply political and shapes the future of urban democracy.
Well, thank you listening, for taking this deep dive with us today. We've journeyed through the invisible, heavily stratified layers of the smart city. We've confronted the structural dangers of digital monopolies, and we've explored the radical, computationally complex but profoundly necessary alternative of a decentralized digital world. The path to a truly smart city isn't just about faster internet. It's about sovereignty, privacy, and community ownership. Before we go, I want to leave you with one final thought to mull over.
Oh, I like this.
We've spent this entire time talking about the digital architecture of the city, but the digital inevitably shapes the physical. If we successfully decentralize our digital cities, how might that change the physical layout of our neighborhoods? If power and data are no longer centralized in massive downtown corporate hubs, could the physical smart city of the future actually look more like a network of self-sustaining, independent villages? Something to think about the next time you walk down your city street, pull out your phone, and look at your apps. Thanks for joining us on the Deep Dive.